So landforms is the start of the last series of discussions for the semester that we're going to have. So each of the following modules is about the lithosphere, and the lithosphere is often considered by a lot of people really the heart and soul of physical geography, where most people who are physical geographers do most of their work, and in that attribute a lot of the other variables that we've talked about, the biota, the atmosphere, the hydrosphere, as a component within the physical landscape of the lithosphere. So often this is the platform for which it gets modified by the other elements, or is the platform for which the other elements is housed upon. So with that, talking about landforms, we need to talk about how they were constructed initially. And in the textbook, it talks about time, form, and formation. And so we've got a really old planet, relatively speaking, here. At the beginning of the semester, we discussed that our planet is 4.6 billion years old, and that when we first discussed its age, we were talking about the cooling of the planet, and with the cooling of the planet, we start to see the formation of the atmosphere. As we have suggested across the semester, that as we continue to lose energy, more and more mass is formed. So we're getting a solid land mass the older the planet gets. So we've had a number of different sequences of landmass appear. A lot of individuals attribute the first large landmass as Pangaea at about 600 million years ago. But Pangaea is not the first of all the land masses to have occurred, and there is geologic evidence that suggests that there were prior megacontinents that were on the Earth. But regardless, the planet didn't start to solidify as one large land mass. It started to solidify as small parcels of lithosphere across the surface of the Earth, and then they formed together to produce larger and larger masses, and then at one time or another those land masses came together, and then they pulled apart, and then they came together again. So what or how this happens is just like putting a pan of brownies into your oven, and the brownies are cooking from the inside out, and the hottest part of your brownie mix is in the inside of the pan. You bring that pan out and you will let that pan cool when the brownies are done, and what ends up happening is the brownies cool from the outside in, as it is exposed to the cooler outside temperatures. So we get this concentric cooling result happening. And so for those of us who like nice warm brownies, we always know that the center of the brownies that have just come out of the oven are at their hottest. So as that brownie is cooling over time, we start to see contraction of that mass start to form, and cracks begin to appear on the surface of our brownie. And as days progress, the outside of the brownie becomes hardest, and then the inside is less and less hard as you progress inward. And finally, as days and days progress forward, then the entire brownie will get hard. So the cooling hardening process happens from the outside inward. We're still a cooling planet. We know that because plate tectonics is still active. We still have geothermal events occurring. We still have volcanoes erupting, and we still have earthquakes taking place. So the current configuration of oldest landmass is seen on this map here with a number of shields. And as you should be able to appreciate, is there is one or more significant masses of oldest rock on every continent on the planet. So some of those continental land masses have more than one, namely South America, Africa, and Asia have more than one. India's got two. Australia has several, but they're small. North America has one very large one, the Canadian Shield, that we'll see an image of a little bit later, and then a few smaller ones. Antarctica has one large landmass. So these large land masses as shields are the platform for which younger and younger and younger land masses start to amass upon. So we're going to consider for now that the Canadian Shield for North America is the oldest and the original land mass, and that is at about 4 billion years old, or at least the rock matter is measured at 4 billion years old. Super stable environment. The longer a rock mass is in place, the more stable it becomes, and that's because over geologic time, the softer, more unstable rock wears away due to erosion and weathering processes. So the material that is most stable is in situ, in place, hasn't been destroyed significantly. That doesn't mean that it's not undergoing erosion and weathering processes. It still is. But this is really just tough rock, and it really does erode very, very slowly. The next oldest material on every continent is then a craton. And that generally, but not always, forms the largest volume of landmass matter on a continent. Together, the shield, the craton, and the subsequent younger material on each continent is known as the lithosphere. And lithosphere is known as the place of mountain building and mountain construction. That certainly is not the case where all of the surface of the earth is a mountain landscape. Mountains are defined very clearly by a number of other terms. So for North America, the Canadian Shield, which is exposed, is illustrated in red here. There are shield material which is occurring across the continent, but is underneath younger rock. If we look to the larger of these two maps, we see all of North America, Central America, and the top of South America. And what we find is the arrangement of rock from oldest to youngest is a lot like tree rings. The oldest stuff often is in the center, and then we've got concentric amassation of younger and younger rock as we move out. So our craton is matter which built from and adjacent to the Canadian Shield, and that's roughly about 600 million years old. The deformed craton, which you see as that fuchsia pink color, if you're astute, you'll recognize sort of makes up part of the Appalachians, and then as we come up the west side, it occupies very much most of the Rocky Mountains and adjacent land masses to the west. The youngest, or the next oldest material, which is in green, the Crescenary Belt, is young mountain building zone. This is currently tectonically active. We've got lots of folding and faulting in this area, as you may be aware of, with lots of earthquakes in California and lots of volcanism in Northern California, Oregon, Washington, through British Columbia, and then Alaska. Certainly that same volcanism and plate tectonic activity is happening through the Baja, down Mexico, Central America, and the western coast of South America. The Caribbean is also volcanically and tectonically very active. The youngest material of all of this is made up of parts of what are eastern Mexico, to include the Yucatan Peninsula, which is important because it's where the meteorite struck the earth that is the defining point for the loss of dinosaurs. We move that across to Texas, across the southern states that border the Gulf of Mexico, Florida, and then a good bit of the coastal plains of the Carolinas, Georgia, and Virginia. Parts of Nova Scotia are also included in this.